Welcome everyone, I'm Norman Wahlberger, and today we're continuing strengthening our understanding of addition. This is actually a relatively simple addition where we're just adding single digits, but we want to go now beyond 20. The addition table, the fundamental addition table, tells us how to add up numbers from 1 to 10 with other numbers of that range, up to 20. But this kind of a wrapping around that's involved extends past 20. So we're moving towards being able to sum up things like this. 5 plus 7 plus 7 plus 7 plus 7 plus 7 equals 40. And ultimately what I want young people to be able to do is the following. To say, okay, the way we approach this is we work from the left to the right sequentially. And I'll show you what we're aiming towards, and then we'll talk about it in step by step later. Okay, so 5 plus 7 is 12. Plus 7 is 19. Plus 7 is 26. Plus another 7 is 33. Plus 7 is 40. Okay, so this sequential aspect, at each stage we're essentially using the basic addition table, but we're involving a wrapping around, which is really going beyond 20. So this is an essential technology upon which our subsequent understanding of more complicated addition is going to rest. Now that basic addition table has a lot of information. It's relatively compressed. It's useful also to show kids that information in different forms, maybe sort of piece by piece. So for example, let's review some important basic sums starting with adding 9. Okay, so if we add 9 to 1, we get 10. That's particularly important because 1 and 9 are complements. Remember, two numbers are complements when their sum is exactly 10. 2 plus 9 is 11. 3 plus 9 is 12. 4 plus 9 is 13, and so on all the way up to 9 plus 10 equals 19. And we may observe here, it's maybe an observation, maybe even a trick, that adding 9 is the same as adding 10 and then reducing by 1. So for example, 7 plus 9, we're adding 9 to 7. What do we get? It's the same as adding 10, which is particularly easy because we just put a 10 in front to go from 7 to 17. And then we come back 1. We reduce by 1. We subtract 1, okay, to get 16. 8 plus 9, up to 18, back 1 to 17. Okay, so if we look at all the additions of 9, then that pattern is clear. So it's nice to look at all of those at the same time and go through each one of them with your young person. Similarly for adding 8, same kind of thing. 1 plus 8 is 9, 2 plus 8 is 10, 3 plus 8 is 11, and so on all the way up to 10 plus 8 equals 18. And there's a similar remark that we could make here. It's perhaps slightly less useful, but you could also think about it that way, that to add 8 to 4 is what you get when you add 10, and then you come back 2. Okay, that's a little bit more complicated, but it's still perhaps worth pointing that out. That might be useful for some students to kind of remember. And one more, adding 7. 1 plus 7 equals 8, 2 plus 7 equals 9, 3 plus 7 equals 10. Those are the complementary pair there. 4 plus 7 equals 11, 5 plus 7 equals 12, 6 plus 7 equals 13, 7 plus 7 equals 14, 8 plus 7 equals 15, 9 plus 7 equals 16, and 10 plus 7 equals 17. Adding 7 is sometimes maybe a little bit harder than the other ones for some reason. Perhaps it's because it's odd or because it's prime, but for whatever reason, perhaps students struggle with this one maybe a little bit more than the other ones. Another kind of little hint or observation to make is that when we're adding a number to itself, like 7 plus 7, that's really the same as multiplying it by 2. Okay, so that's something that people should be aware of. 7 plus 7, same as 2 times 7. They might remember that more easily. Another thing to keep in mind when you're working through all of these is this underlying rule about the way additions work with even and odd numbers. That an even number plus an even number is always even, while even plus odd is odd, or odd plus even is odd, same thing, while odd plus odd is even. So for example, if you're adding 7, 7 is odd. And that means that the process of adding 7 will take an even number to an odd number. Like 6 plus 7 is 13. 6 is even, 13 is odd. While it takes an odd number to even. 5 plus 7 is 12. 5 is odd, 12 is even. So that's something that also that students should just be aware of at the back of their minds to help them reinforce things. And maybe as a bit of a check, like if you get 5 plus 7 is some odd number, there's something that should jar there. Students should recognize, oh, there's something wrong here. Now I've talked about the easy half of the addition table and the harder half of the addition table. The easy half involves sums that are only up to 10, while the harder half involves sums that go beyond 10. Okay, so the harder aspect involves wrapping around 10. And we have to get our head around that because exactly that same kind of thing is happening when we go beyond 20 to higher numbers. So here are two examples. So if we add 3 plus 5, we get 8. And geometrically, there's 3, there's 5. We put them together physically in terms of these row rectangles, and we get 8. No modification is needed. However, when we do a harder example, like 7 plus 5, okay, that's going beyond 10. Here's 7, here's 5. When we put them together, we don't want to just put them together and get a big, long rectangle because it's hard to appreciate how big that rectangle is. So in our minds, what we can do is we can take the 7 and take 3 of these ones to form a 10, and then there will be 2 left over. Okay, so that we call this wrapping around 10. So then we get 10 plus 2, that's identifiable as 12. So this is a geometrical interpretation or visualization of what the actual entry in the addition table is telling us. Okay, 7 plus 5 equals 12. And this geometric technique, happily, works for sums beyond 20. That's one of its advantages. So now let me illustrate that by having a look at two variants of those examples that we've just looked at. So let's look at 13 plus 5 now instead of 3 plus 5. So 13 plus 5 is 18. And here's a visualization of it. Here's 13. It's 10 plus 3. So we've written it this way instead of in a long row rectangle because it corresponds better with our Hindu-Arabic representation of the number. And here's 5. And when we add them, we have to juxtapose these two things. And we can do that simply here by just taking this rectangle and slotting it down in the second row beside the 3 that we have here, giving us 10 plus 8, or 18. And now consider 17 plus 5, which is kind of a bumped up version from 7 plus 5. So 7 plus 5 equals 12, and now 17 plus 5 equals 22. And have a look what's happening here. So here's 17, again in this 10 table formation, where we have a row of 10 followed by a row of 7. There's 17, and there's our 5. So to add them, what we're going to do is we're going to take part of this, actually 3 of them, and slot them beside the second row here to finish that row of 10, to make a complete row of 10. Then we'll have 2 left over, which will go down to form a new row. Okay, so altogether we get 10, 10, 2. So 2 10s and 2, otherwise known as 22. So it's really the same kind of thing as what was happening when we were adding just 7 plus 5, but there's now an additional row of 10 hanging around. But what we're actually doing otherwise is exactly the same. Now remember that earlier in this series, we introduced a little bit of a convention that instead of writing out long row rectangles, we had these sort of shortcuts using colored squares. So we had a convention that our red square represented a row of 10 ordinary squares. Okay, so this is a more compact unit for representing 10, which accords nicely with our Hindu-Arabic system. So this allows us then a more compact way of looking at the computations that we've just made. So let's have another look at 13 plus 5 equals 18, where now we're representing 13 much more compactly with this form here. Okay? There's a single 10, a red square that represents 10, and 3 more. Okay? And here's our 5. And then again, geometrically, we can still perform our juxtapositions with these things. We put this 3 and this 5 together, forming that little row there of 8. So we have a 10 and an 8, and that indeed is 18. And the other thing that we did was 17 plus 5 equals 22. So here's a more compact way of representing 17. A 10 here and a 7. There's the 5 again. We do the same wrapping around. We take 3 of these, add it to the 7 that we have to form a long row of 10, and the other 2 come down. But now this row of 10 actually doesn't have to be there because we can replace it with a single red square. So this is a shorthand for what's happening. 17 plus 5 equals 22. 10, 10, and 2. So the initial wrapping around 10 that we started with can be extended to wrapping around 20, but also wrapping around 30 and so on. So let's show you how to do that. So here, for example, is 1 plus 3 plus 5 plus 7 plus 9. Let's say we have to add up this sum. So this is the kind of thing that I want students to be able to do mentally, first of all, and I want them to do it by proceeding from the left to the right methodically. Okay? And so in our minds, what we would do is we would say, okay, 1 plus 3 is 4, plus 5 is 9, plus 7 is 16, plus 9 is 25. So at each stage, we're doing a single addition of a digit to whatever we already have. So at this stage here, we had 16, and then we added 9. So 16 plus 9, that's like a wrapping around, because 6 plus 9 is 15. And so 16 plus 9 will be 25. We can visualize the entire summation using a 10 table. So here's 10, 10, 10, part of perhaps a column of tens. And we can visualize what's happening by making little rectangular bars. For example, here's 1. Here is 3. So this bar here represents the row rectangle 3. Here is 5 in red. Now the 7, though, is split. So it starts here, that's the first one, and then there's 6 more over here. So it's wrapping around 10. So here, up to here, we've got 16. And now we have to add 9. Again, another wrapping. So we have 4 of the 9. And then there'll be 5 left over. The 5 left over go on to a new row, giving us altogether 10, 10, 5. 2, 10, 5, or 25. And more compactly, then we can represent the end result as a 10, 10, 5. 2, 10, 5, or 25. So I want children to be able to work these things out mentally. That's very, very, very important. Okay? But I want them also to have this geometrical understanding of what's going on, and I want you to use this as the geometrical underpinnings of what's happening. Okay? We're making manipulations with boxes which represent natural numbers, and we're stacking these boxes sort of systematically down in an organized fashion of width 10. Okay? At least until we get to 100. Once we get to 100, we may have to think about something a little bit more complicated, okay? But at this stage, that's what we're doing. Okay, there's now a whole important suite of exercises that young children can be given to strengthen their understanding of this fundamental operation of being able to add successfully lots of digits one after the other. So for example, 4 plus 8 plus 9 equals something. What they want to do is 4 plus 8 equals 12, plus 9 equals 21. And why is it 21? It's because 2 plus 9 is 11. So we're wrapping around. The 2 plus 9 is 11, and we also have a 10. So we have a 10 and an 11, that's 21. So we're wrapping around the 20 instead of wrapping around the 10. 6 plus 5 plus 4 plus 7. 6 plus 5 is 11, plus 4 is 15, plus 7, now we wrap around 20 to get 22. And the fundamental addition thing that they're using there is 5 plus 7 equals 12, but now it's at the level of 15 plus 7 equals 22. And more such things. So I want you to teach your children to work from left to right systematically. Okay. For example, for this one, you might be tempted to say, well, why don't we sort of rearrange things in our mind? Maybe we combine the 1 and the 9 first to make 10. That maybe would be simpler. No, I don't want you to do that. Okay? I want them to work from left to right systematically, completely indifferent to what the numbers are. We're going to work systematically and we're going to do it in the same fashion every time. Okay. Now, of course, associated with any one of these mental calculations is a possible geometrical picture, a representation of slotting these row rectangles together to form this increasing pattern of boxes, 10, 10, 10, and then whatever you have. Okay, so as a kind of a corresponding exercise, illustrate the above calculations using a 10 table. For that, we need a prior piece of graph paper, suitably maybe enlarged a little bit to allow people to write inside. And then we can go further. It doesn't have to be 3 or 4 elements. After a while, 3 plus 6 is 9, plus 9 is 18, plus 4 is 22, plus 2 is 24, plus 1 is 25. Okay, exactly that way. 3 plus 6 is 9, plus 9 is 18, plus 4 is 22, plus 2 is 24, plus 1 is 25. You can even get them saying it. Okay, and then we write down 25. So to get students from just the basic addition table to doing something like this smoothly is a lot of effort. That's really takes some training, okay? Some training, repetition, and you have to motivate students, maybe play some games, have some competitions. You know, that's the educational side of things. How you're going to get your students to enjoy learning this technology is another question. Okay, but I'm trying to explain to you what it is that you want them to end up being able to do really smoothly and accurately. In our next video, we're going to go beyond this, same direction, but to start thinking about arithmetical sequences. Generating arithmetical sequences, which are particularly kind of regular patterns like this, in a systematic way. That's also a really important development. Okay, so I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.